All right. Looks like the last couple of people are walking in. Good morning, everyone. My name is Andy Bette. I'm a principal product manager for Amazon DynamoDB. And I'm excited to introduce today Tejana de Zoysa and Chris Osler from Venmo. And they're here to talk about the data architectures that they implemented to keep up with the rapid growth of Venmo's business. After a short introduction from me, they will tell you a little bit more about the company before explaining their overall architecture and then discussing 3 projects. The first is the database migration for their social feed, implementing their transaction history stream, and moving to an event-driven architecture from a nightly batch. So some of the things that we hope that you'll get out of this session are the ability to compare your design with what Venmo successfully implemented already, confidence that the things that you plan to try have been effective elsewhere, and ideas about how to approach similar projects in your businesses. Can I get a show of hands? How many folks here are from the financial services industry? It's about a good number. It looks like a third, maybe more. You're all in the right place. I hope everybody else is as well. You're joined by a number of colleagues from across the industry, from trading to insurance. Because of the critical nature of the workloads that you're running and that a lot of you are here to hear about, if you're not in the industry, we see customers using a variety of AWS capabilities, from dozens of compliance programs that we support, fine-grained access control, event-driven data processing, and data sovereignty no matter where you do business. And some of the things that our guest speakers are going to cover today are how they scaled up infrastructure in order to match growth of customer usage, how they designed their architecture to handle bursts of traffic, and how they were able to achieve those improvements in performance at a lower cost than with their previous architecture. Now, in case you're not already familiar with the services that we're going to talk about today, I'll just quickly review some of them. First is Amazon Aurora, which is a global-scale relational database service that provides high performance and availability with full MySQL and PostgreSQL compatibility. Second is Amazon DynamoDB, the service that I work on, which is a serverless NoSQL database that provides single-digit millisecond performance at any scale. Third, Amazon Kinesis Data Streams, which is a serverless streaming service that makes it easy to capture, process, and store data streams at any scale. And finally, Amazon Kinesis Data Streams, which is a serverless data streaming service. And finally, Amazon Document DB, with MongoDB compatibility, which is a serverless JSON document database, which allows you to store and process documents at nearly any scale. For further reading after today's session, please take a quick look at these QR codes. You can take a photo of them now. They link to useful resources that you can read more on all of these services, as well as example architectures. I'll give you a moment to do that. All right. And with that, I would like to welcome Tejana de Zoysa, Director of Engineering for Venmo, as well as Chris Osler, Principal Engineer for Venmo, to dive into some of their work. Please give them a round of applause.
Thank you, Andy, and very good morning for all of you guys. I'm going to be starting things off by giving a very quick introduction to our business before we get on with the technical content. Venmo was founded by 2 new college graduates who wanted to find a very simple way to share expenses with their friends and colleagues. So initially, they started this off as a very simple SMS or text message-based peer-to-peer payment solution, but now it evolved into the mobile application and the Venmo.com website that you see out there. As any other startup, the beginnings were extremely humble. The use case was simple, me sending you money. And to do that, they implemented a simple Python application, a Django application that talked to a MySQL backend. And it did its thing, right? We had some volume going over it, and the business was growing. However, over time, Venmo grew in popularity. And now it has become a product that's used by millions of users in the USA. And also, it has earned the verb status. When I say verb status, I want to check something. Show of hands if you have used the phrases, I'll Venmo you or Venmo me in the past few months. Okay, that's proof. Thank you. And also, Venmo is mentioned in social media every 2 seconds. We started small, we had growth, and now we have over 60 million monthly active users who engage in our platform and use it every day. You heard a lot about peer-to-peer in the beginning of the presentation, but we are more than a peer-to-peer company. We offer a wide variety of products. If you hold a Venmo balance, you can instantly cash it out to your financial institution, which is your bank. We have a debit card. You can swipe at a merchant location, purchase goods using your Venmo balance. You can get your paycheck deposited into your Venmo balance. You can buy, sell, hold cryptocurrencies in the Venmo app. If you're a small or a medium business and if you want to accept payments, we have solutions for you. If you're a large retailer and if you want to have Venmo as a funding instrument in your pay sheet or in your checkout screen, we do offer a solution for that as well. You can create a group in Venmo for your group of friends, split and view expenses. You can scan a picture of a check and deposit into your Venmo balance as well. So I'm going to be wrapping up the intro with some final metrics. I mentioned 60 million monthly active users earlier. We have 90 million annually active users who engage in our platform. We process more than $1 billion a day, and that translates to millions of transactions every single day. And there are certain days where we get burst traffic and extremely high volume as well. We add $18 billion of net new funds into our ecosystem every month. And we have a highly engaged user base where they interact with our app at least 12 times a month on average. So we wanted to share this high-level overview and show the scale before we actually dive into some of the problems that we faced as a company with this growth that I just mentioned. So with that, I'm going to hand this off to Chris Osler to talk about our high-level architecture.
Thank you, Tejan. Thank you, everyone, for the welcome. I have to say, all the presentations I usually do are internal to a company, so I never get rounds of applauses. So this certainly has its perks. I appreciate that. Tejan went and talked about kind of the growth of Venmo. And so kind of our theme that we want to go over today is that scale changes everything. That's one of those very good problems to have as a company of having to deal with the challenges of scale. And so as we go through, we want to spend some time. I'm going to go and talk through how our architecture's evolved from that very simple beginning that Tejana showed. We'll get into some details of some specific things we've done in changing that architecture. But throughout that, there's really two key themes that we want to talk about here. And these aren't going to be earth-shattering. The first is that in dealing with this scale that changes your architecture, changes the way that you approach your business, your organization, one of those technical strategies is you're trying to distribute your load around so you can maximize your throughput. And so we'll talk about some of the ways where we're approaching this either from centralized resources or other ways that we're trying to distribute that load. The second key strategy we want to talk about is being able to use event-based systems so you can find processing that doesn't have to be on your critical path and distribute that out again, temporally this time, instead of having it in that critical path, being able to do that in the background or asynchronously, again, as a way of distributing that load out. And so as we do that, I'm just going to go through and we'll talk about this evolution of our architecture. We'll talk about some of the changes that we made, and then get into some details of how we're able to pull that off. So here's that graph or the design that Tejana showed, just the simple Django app that was talking to a MySQL database. In this situation, in our early days, we were just running both of these on raw EC2 instances. As we grew, it was easy enough to scale. If we had more traffic going through the app, we just add a few more instances. The database was able to support a fair amount of traffic. When we started reaching capacity on that, we're able to upsize the instance and vertically scale that. It was a great way to grow the business. It was very successful. If you go back to your very first database class in college, you might remember that, I remember in my class, the first introduction was, well, we need to transfer some money from Alice's account to Bob's account and make sure that we do it right and we don't lose money or invent money. That use case for a relational transactional database was exactly what we were doing, and so that was a great solution for what we were trying to accomplish. What we found is then we identified some cases where there was processing that was happening in that critical path that we didn't necessarily need to do while a user was waiting. And so we introduced celery queues to our application where we could essentially defer application handling and to be able to happen at a later point in time asynchronously. And so we spun up a second set of worker instances that all they did was process these queues that weren't taking the direct customer traffic. And so this is kind of our first pass into utilizing some events. And this gave us a couple of things, not only the latency and the scaling benefit for the users interacting with our system, but it also allowed us to give a little bit of decoupling. Some examples are maybe we have a team that's processing a money transaction, and we have another team that's handling user interactions with notifications or email messages. Using that celery queue in between, not only does it move that processing of notifications or emails outside of that payment critical path, but it also means that another team can focus on just that functionality and not have to be aware of all of the functionality within the Venmo application. The next thing that we did is as we're growing, we recognized that there's a lot of queries on our database that don't necessarily need to be handled by that writer instance. And so we introduced some reader instances. This is a way we're able to distribute some of that load, move it off of this shared writer instance onto the reader instances. And so this was just giving us a little bit more capacity. It allowed us to scale up that vertical database a little bit larger with the transactions that we're processing. As we continued to grow, we started adding these use cases that Tejana was talking about. Here's additional functionality being introduced into our application. And we recognized that some of those use cases didn't have to have the same transactional interactions with the core user data that we had in that MySQL database. And so we started being able to introduce additional data stores that were perhaps better technological matches for these use cases, but also isolated in that they weren't part of that same shared resource, and so they could scale independently. And so we started getting things moved into the application like our DynamoDB, some MongoDB, some OpenSearch that were functioning and serving specific use cases of different traffic. Following that trend, as we grow as a business, you get a lot more interest in being able to look at user behaviors and track patterns and do analytics. These are query patterns very different than what your user-facing transactions are. And so being able to service those in a way that's different than the user transactions was also very beneficial. And so we're able to set up some replication. We're replicating that data out to separate database instances that were indexed and tuned separately to be able to handle these analytics workloads, which were so much different than our online processing. And so then we get another instances of MySQL for analytics. We started building up a data lake. And again, this is figuring out where we can shift traffic off those shared resources that are the bottlenecks and the critical points for our user interactions. As we continue to grow, we're recognizing opportunities to have more independent work streams within our architecture, and we started introducing some microservices. At this point, we have the celery queues that we'd used before were great for talking from one application to another, but there was a coupling within the application there. And so being able to speak from one application to another, we introduced Kafka queues. And some of these microservices also introduced their own data stores, particular to their use cases. And so we started getting more technologies coming in. We had Cassandra. We had some others that come in. And so as well as kind of our synchronous dependencies between our main application and our microservices, we have these asynchronous Kafka streams. This is just another step where we're figuring out how we can share that load and spread it around architecturally. This gave us better scaling opportunities, but as you can see from the diagram, it continues to get more complex as there's more components to be aware of. Again, this qualifies as one of those good problems to have as a company, where your drive to improve and to scale is driven by your customer needs, and so that complexity is worth the value it's bringing to be able to support that. As we continue, though, we still have this centralized shared database that is kind of our core place for a lot of our user interactions. And so even more recently, we've started identifying places where we have data within that core database that doesn't necessarily need to have the same transactional relationships with the rest of the data. And so when we can identify use cases like that, it gives us an opportunity to move those over into a different instance. An example of that is, one of the workflows you do is you're transferring money out to another financial institution. There's some offline workflows that are happening with ACH transactions where we're tracking that. But the user doesn't need the same transactionality with that. They know that this transfer request is in process. And so there's examples of things where we can take that and shift those loads out to a separate data store. One of the other steps that we took is recognizing some of our data store dependencies we've been running on kind of our own instances on top of EC2 or other technologies there, where there was opportunities that we had to move to managed services offered by AWS that reduced the load that we had on our internal teams. And so that let us focus our efforts on places where it was really important to the customer rather than the low-level infrastructure things. And so in places where it made sense and was operationally feasible, we have moved over to managed services to simplify what our operational workload looks like. Through all of this, though, this default database, this beginning database we had with our Aurora instance, continued to be the place where we would add additional use cases, as well as where there would be a lot of growth. Just the organic growth on our payments processing as the business grew, the numbers that Tejana showed with our numbers of users. And so that introduced some challenges. We have certain constraints with how we're able to keep up with replication. So as we do maintenances or database upgrades, we have constraints on how we're able to approach those. We have certain periods where we expect higher volumes of traffic. We know and expect that there'll be sustained increases. And so that also puts some strain both on our systems as well as the replication. And we have additional high-volume events where we know that there's going to be expected spikes, where we recognize, okay, these shared resources, as much as we've been trying to distribute them, still become kind of the limiting factor on how much traffic we can take there. And so as that database continues to grow, back to these themes of distributing our load and looking for ways that we can move components out of our critical path, that continues to be one of our focuses. How can we keep moving traffic and volume off of that shared resources onto some other systems? And so as we go through the rest of our presentation is get into some specific projects where we're doing that, where we're looking at how can we move certain functionality and be able to shift around, do it in a way that allows us to make the guarantees we need to around our customer experience and around our data integrity. So we'll turn over to Tejana to talk through our first instance of that.
Thanks, Chris. So the first use case we'll cover is called the social feed data migration. I'm going to first explain what the Venmo feed is for all of you guys. Feed is what makes Venmo social. This has transaction visibility that you had with your friends. Every single transaction generates what we call a story. And also, it includes certain profile change events, like you subscribing to crypto. To get the terminology correct, because I'll be referring to these terms on and off in the next few slides, story is each line item that's generated for a transaction. Feed is the capability. This is an extremely high traffic endpoint because this is our home screen. When you open the app, you land on the feed. And also, it generates tons of data every single day because of our sheer transaction volume and our customer base. So this is a screenshot of the feed that you can see in this slide. Now let's talk about the problem. We had the feed housed in a monolithic Mongo cluster alongside 40 other collections. Stories had one collection, and there are 40 plus other collections in this Mongo cluster. And we had 5.6 billion stories in this collection, and also 3.6 terabytes, which is quite large. And also, since this being a tier 1 service and our homepage, we expected single-digit response time, query response time from our data sources. Stories was pretty much taking up the capacity of this Mongo cluster. It was eating up 90% of the memory, and also 65% of the storage was also consumed by this. And this was certainly not a budget-friendly option because we had licensing cost. On top of that, we had infrastructure costs with the rapid data growth as well. And most importantly, this was creating noisy neighbor problems, meaning if one Mongo collection was having a slow query, feed, which is our home page, was getting impacted, and vice versa. So this was an architecture that we wanted to move away from as we saw growth. So we evaluated different database technologies, and we ended up picking Amazon DynamoDB, and the reasons are here. One of the reasons being cost. Like I mentioned earlier, we had licensing costs as well as infrastructure costs on all of the EC2 instances to store the data. And we found that this option to be 90% cheaper than MongoDB. We were looking for a DB platform that could provide the same performance, single-digit millisecond latency, and also support the data growth and the scaling requirements that we had. And most importantly, we've talked about managed services a lot previously. It was important for us because then we could actually deploy our engineers to focus on business problems that matter without having to worry about patching infrastructure, etc. And as a financial organization, data encryption at rest is a requirement for us. It's a compliance requirement. So DynamoDB provided that straight off the bat. And we are already integrated into AWS pretty heavily, and things like automatic backups, access control via IAM, all of these things made the integration seamless. Now we're going to talk a bit about how we did this complex migration, because this is a tier 1 service for us. It's our homepage, and we have to be very careful on how we do this migration. So first thing that we did was we've created a DynamoDB, a single table. We've looked at all of our read paths and created secondary indexes to optimize for our read paths. And we created a backfill job that takes the data from our Mongo infrastructure and translate it to the new table format that DynamoDB understands. So, and we executed this. And in parallel, we invested on dual writes. So while we write to MongoDB, we continue to start writing everything new, which we call the front book, into DynamoDB. So this helped us immediately verify the performance under production load. Can DynamoDB handle our scale? That was a question that we wanted to answer immediately. And also, if we run into any data consistency issues or bugs are normal in any kind of an integration that you do, we could actually use this backfill process to get the data into a consistent state as well. The next thing that we did was, once we are comfortable with our backfill and we had all of the data for the length of the period that we were interested in, we slowly started ramping reads. Since this is a tier 1 service, we don't go like 0 to 100% on a feature like this. So we gradually increase the ramp from 1%. 1% of the users will actually start reading from the Amazon DynamoDB and the rest of the 99% will go into MongoDB. And we gradually increase the ramp by looking at the performance, looking at bugs, looking at customer reports, all of that. And finally, once we verified that the system is performant, there are no bugs, we're happy with the performance, then we could actually stop the writes for MongoDB and completely cut ties and deprecate that infrastructure. One thing I'd like to highlight in this ramp process is this helped us validate the performance and also fix any data consistency issues, and most importantly, back out of this migration if we were not happy with any of these services or any of the changes that we were doing without having any negative customer experience for our customers. So that concludes the first use case, and I'm going to hand it back to Chris to talk about our second use case.
So if you guys remember from the diagram I was showing earlier, we reached a point in our architecture where we started introducing microservices. And so I wanted to talk about one of those microservices, which was a history service. What we had set up is we had a Kafka queue that every time there was a payment event, we'd put a message on the Kafka queue. That would go to this history service, and it was able to read that and put it into a secondary data store that was in Cassandra at the time. And so this was giving us a way where we had a secondary data store that we could use for certain use cases within the company. That was offloading load from that shared Aurora MySQL instance. The challenge that we ran into is that when we implemented that Kafka stream, it was done as a best effort publishing. We'd go through, we'd perform our transaction, we'd commit it to the database, and then we'd write a message to the Kafka queue. On top of that, there were some additional optimizations to try and minimize the load on the application, where those were being bundled in the background and then sent as a batch. The result of that is that we didn't have any guarantees around the fidelity of that Kafka queue. And if that was our source for putting those records into that historical database, we couldn't make a guarantee about having 100% of that data. And so as we grew, we wanted to move additional use cases over to that had those requirements of having full fidelity data. And so looking at our options, we were trying to consider what we could do to get that. The first logical option in looking at it is the Aurora products offer a database activity stream. Looking at that, we were using Aurora MySQL, which only offered an asynchronous stream, which also had the same lack of guarantee around the fidelity of that. So we looked at other options. We could move and shift to a publishing first. Instead of committing the transaction first and then sending a message once that had done, we could try sending a message preemptively, and then as so we'd be guaranteed to always get a message. The challenge there is if you have a message, you didn't have a guarantee whether it had committed to the database. And so in reading that message, you'd have to go and compare back to your system of record in order to figure out if that was a committed message or if something had happened before that had actually committed to the database. So while giving that the fidelity that we needed, it also introduced additional load on that system of record, which is what we were trying to avoid in the first place. We could have done a solution where we had some custom processing of the bin logs from our database, where we could get from that a guaranteed event stream. The challenge there is that would couple us exactly to the MySQL instance in their bin log format. What we ended up doing is we looked at another option of having a write-ahead log where we could get kind of the same effect of only having to validate possibly missed messages. The benefit of that over the bin log handling is it's not something that was coupled to the storage technology, and it was something to be able to apply to some different scenarios. So I want to talk a little bit about how that happens. The first thing we ended up doing is, as we went to process one of these requests, is instead of beginning our processing, we'd first just write a log message saying that we intended to perform this action, and we stored that in DynamoDB. That gave us the durability on these that we needed, as well as a separate data store that didn't have any impact on what our main system of record was. After we had written that intent to perform this action, we could go ahead, process the transaction as we usually would. Once that had been committed, we could publish our message out, just as we usually had before. Then as a final step, we would just go back to where we had written out that intent and delete it from the database saying, hey, processing has been completed. The result of that is then anything that was left remaining in that DynamoDB database, one of two things had happened. Either there had been some type of a failure and we hadn't committed that transaction, or we had committed that transaction but hadn't been able to publish that message. And so then we could add a simple process that would just sweep that table in the background, and for the records remaining in there, could do that validation step against our system of record to figure out if it had been committed or not. If it had been committed, then it would just go ahead and publish that message so that we'd be guaranteed an eventual consistency on those messages so that we had complete fidelity on what was coming out of that message stream. The benefit there, though, is that validation against our system of record only had to happen for that very, very small subset of messages that had left an orphaned entry in that processing table. And so instead of introducing a validation load of 100%, if we had moved to a publish first model, instead we could have a validation load of 0.001%, which was certainly something that we could introduce. That load wasn't going to make or break our application, but it gave us the guarantees that we needed in order to be able to start building systems off of this history. The other nice thing of that is that it's a pattern that was able to be applied in different ways. For our messaging, this brought us from 4 nines of guaranteed messages coming through to a complete 100% fidelity. But there's other places we're able to apply it. We have certain transactions. When you go and you swipe a debit card at a merchant, we have to go and we get a message from us, and we have to be able to either approve or deny that transaction. And so we'll go through, we'll check your balance, make sure you have the appropriate balance for the transaction, and we'll go ahead and hold that balance and keep it, and then approve that transaction. And the other thing that we do there is we run a bunch of risk checks to make sure it's a transaction that we believe to be valid. In those situations, you have a customer who's waiting at the point of sale terminal, waiting for that response to come back. So that latency is a very critical factor in that. And so what we found is we could use this same write-ahead log pattern to help us in those scenarios to be able to parallelize that. And so instead of first running our risk scenarios and only once those completed begin processing the transaction, instead we could optimistically run both those in parallel. We could kick off our risk, start the processing of that transaction. Then once we completed, we could validate that, hey, if the risk says that was approved, we want to leave this transaction in place. If the risk says we should deny this transaction, we need to make sure that gets rolled back and not committed. By being able to use the same write-ahead log pattern, we could guarantee this consistency between those two actions. Rather than be an action of committing a payment to a database and processing, publishing a message on a message queue, the two things that we were coordinating was completing the risk transaction, or the risk evaluation, and writing that transaction to the database. So being able to parallelize those two gave us latency gains. In one situation, it was able to bring our P99 down by 34%, I believe it was, and another by 23%. And so being able to gain those latency was a direct impact to our users as they're standing there waiting for that response at the point of sale terminal. As we continue to go and separate out our database, so I talked earlier in that architecture about finding places where we can move data out of that shared instance into independent, isolated instances, we have similar patterns of needing to coordinate two things. We have perhaps related writes where we're needing to write into a shared instance, as well as do a related write into an independent instance. And the same pattern is able to help us solve those solutions as well. It essentially gives us kind of a Saga-light design pattern that we're able to apply in many different areas. And so by being able to do something that was more generic, it gave us the opportunity to have that pattern to fall back on and use in lots of different places.
So the next use case that we're going to talk about is asynchronous payment processing using Kinesis. This is our final use case as well. First thing I'm going to do is I'm going to go over how a card transaction works with this audience, and then we'll go into the problem and the solution. So I'm going to use the Venmo debit card as an example here. Let's say, as a customer, you want to go and pump gas to your car. First thing you do is you will pull in, you have to take your card out, and you have to insert it into the fuel pump. And at that point, something we call the payment authorization, or auth, happens. So the gas station forwards it along to the card networks. Card networks look at the first 4 to 10 digits of your card number and figure out, oh, the issuer for this card is Venmo, so I need to route it to Venmo. So when Venmo gets it, we do things like risk checks. We write it to our SOR, and we would hold your balance. And we acknowledge back to the upstream systems. And this operation is synchronous. So the gas station receives it, and they do their processing, and they unlock the pump for you. As a customer, you pump gas, and you drive out. But even after that, there are certain things that happen in the background. So generally, these auth transactions are for a higher amount. They might do an authorization for like $80. But the amount that you end up actually filling gas would be $65. So that is, then they have to actually follow up with a capture message. And these captures, the card network receives it, they do the same thing. They route it to Venmo, referring to the original auth. Go and charge the person $65. At that point, Venmo takes this transaction, makes that hold permanent, actually debit the user's balance, update our SOR, do our processing, and respond back. One interesting thing is these captures are not synchronous. They are not real time. They are happening as batches most of the time at the end of the day. And what used to happen is we get these batches as a huge burst of data into our systems. They're hitting our APIs. They're going through transactions sequentially in this batch, and they were hitting an API, a synchronous API that Venmo has hosted on our end. So this shows how we've kind of processed it. There's the card networks, there's the Venmo platform, and we were processing these payments just like any other transaction that we had in Venmo, like a peer-to-peer payment or a payment, Venmo debit card, or transactions. All of the processing was synchronous, and we were using all of our shared infrastructure, the Aurora database, our document DB, our caching infrastructure. This was not sustainable for us. One, these batches are huge, and we did not control the time that they came in. It might come in at peak volume for Venmo, and also it might have transactions bundled up for 2 to 3 days sometimes. And we had hundreds of thousands, sometimes millions of transactions in these batches. And when this happened, it was slowing down our processing. We might have commit delays in our relational database. It might overwhelm some of our systems. So these are growing pains. We've stood up a synchronous processing endpoint when we were a small company, but our volume grew, and we could not sustain the volume with our current architecture. And also, one important thing I'd like to mention is these messages that we get from upstream are must-honor transactions. We cannot say, no, I can't process it, because the goods or services have already exchanged, and the customers are no longer present, and we have to process these transactions. If we are not able to do it, we have to find ways to reconcile with upstream systems and process them. So if Venmo were to have some kind of a blip, well, let's say we had an infrastructure outage or any kind of application bug, we can't send 500s down upstream. Even if we did, we had to spend a lot of time trying to reconcile the two systems, upstream and ours, and make the merchant and the customer whole. And also, being able to, initially we didn't have a way to replay these transactions automatically. We always had to work with these upstream systems, like I mentioned earlier. And there's not just captures in these batches, there's other message types as well. Refunds also come in as batches sometimes, and there are other message types called advice messages. So as a solution, we didn't ask any of our upstream systems to change anything. They continued to behave the way they do today. It's business as usual for them. They would still take up their batches. They would still hit Venmo at the rate that they used to. And what we did was we implemented an extremely thin API layer that consumes the message from the network and put it into a Kinesis data stream and acknowledge it back to upstream system saying, success. So at that time, when we did that, the upstream system saw a huge improvement in latency because we are not processing any of these synchronously. And from Kinesis, what we did was we stood up a whole bunch of consumers that would take on messages, DQ, from the Kinesis stream and process the way that we used to. This architecture helped us throttle the transaction processing volume that we were getting so that we don't overwhelm our systems and also handle high volume events gracefully. Two things I'd like to highlight here is we use external customer ID as our partition key for our Kinesis streams. One important reason is message ordering is important to us. That's one reason we went with Kinesis and not SQS. As a financial company, if we got certain transaction in an order, we'd like to write it to our ledger in that order. Second, with our volume, we see tons of collisions. When I say collisions, concurrent transactions. Me as a customer, I could get my balance updated by 2 separate transactions. So we'd like to avoid that. So by partitioning by the customer ID, we could put the transactions in sequential order for the same customer as well. And also, we are using enhanced fan-out consumer capability in Kinesis in order to process certain message types with a higher priority. For example, refunds, we don't want to wait. We want the refund out to our customers as soon as possible. So we would process them with a larger set of consumers, more in a near real-time fashion, versus some of the messages like advices, where we could take a little longer. And final thing I'd like to highlight with this architecture is we implemented it in a way that it's self-healing. Let's say if we were even to have an outage or some kind of a blip downstream, we would automatically go into a DLQ, and these messages will be redriven into Kinesis using a reconciliation mechanism that we've implemented. So right now, with this architecture, we do not have any kind of manual remediation, paging engineers, or bothering them on comparing SORs. It's all self-healing, and it's able to handle the throughput at the rate that we are comfortable with without overwhelming any of our systems. So that concludes all of the use cases that we wanted to cover today. So our closing remarks for today is scale changes the approach to architecture. In the beginning, you saw we started off as a monolithic application and as a data monolith as well. But soon we realized that's not going to work. There's load coming in, we are overwhelming systems, and we have to think about decentralization and decomposition more and more. And also, we've talked about decentralizing load to improve throughput and also to reduce choke points or bottlenecks. And with that, we've created this distributed system, and the cost here is architecture complexity. Now we have a big distributed system. All of you know, managing distributed systems are complex. If you want to do a large change, you have to do some coordination. So that's the cost with that approach. And also, event-based systems offload processing from the critical path. In the Kinesis use case, we made upstream systems happy by having a low latency operation and immediately responding back. We are making processing more efficient, but the cost here is eventual consistency between systems. It takes time for the systems to come into a consistent state. And also, you need to invest on things like remediation or reconciliation frameworks in this process. So with that, all of the use cases, those are all of the use cases that we want to cover today. This is how Venmo addressed rapid growth over time, and some of the architecture decisions that we made to battle growth. And we believe there's other ways to do it. And these are just some of the 3 use cases that we handpicked for this session. But there's many that we run into day in and day out. And we are going to be hanging around here for a while after the session. If you have questions for us, come talk to us. If you want to share your ideas, come and talk to us as well. And also, I'd like to thank AWS, our partner, for giving us the opportunity to come here and share our use cases with all of you. And architecture, we believe, needs to evolve as well, because we are constantly adding things to our roadmap to support the Venmo's future growth. And I think I'm going to hand it off to Andy to close out the presentation. Thank you.
Thank you, Tejana and Chris. Give them one more round of applause, please. Just wanted to remind everybody that you can sign up for Skill Builder accounts to do testing and learning. And you can see the URL right up here, as well as contact information for us. So you have my email address up there if you have any questions about any of the services that you heard about today. And Tejana and Chris and I will all be here on the side of the room if you have any questions.